Okay, now that we have an understanding about how to assess the uncertainty of our parameters, how do we incorporate those uncertainties and come up with an estimate of the reliability and the probability of failure when performing a slope stability analysis? So to do that, we first need to come up with two numbers. One is the FMLV, the factor of safety for the slope using the most likely values or the averages. Now this is really straightforward. We know how to do this. You just take the mean parameter values, or the most likely values, the averages, and then run a traditional limit equilibrium slope stability analysis, and that factor of safety you get is the FMLV. But then the next part is what gets a little more tricky. Then you have to come up with the coefficient of variation for the factor of safety. And in other words, given all the variation in the input parameters, what is the variation in the resulting factor of safety? And if we can come up with that, then we can, there's an equation we can use to calculate the reliability and the probability of failure. And in this process, we typically assume that the factor of safety is log normally distributed. And again, once we have the FMLV, the factor of safety computed using most likely values of parameters, and then the COFV, the coefficient of variation for the factor of safety, we can use this table, do a double lookup, and calculate the probability of failure. And so there's a relationship, or there's a mathematical relationship between the probability of failure and these two terms. You can also scale it off of this diagram, meaning you start with the FMLV on the bottom. You come up to the proper coefficient of variation for the factor of safety, and then go to the left and you get the probability of failure. This graph here is simply another way of representing the same data that is shown in this double lookup table. Or what is more typical is we just do a calculation in a spreadsheet, and both that table and figure basically are a graphical representation, or tabular and a graphical representation of an equation, or a set of equations. And so this is based on something called the reliability index beta, which is the number of standard deviations between the factor of safety and the most likely values and the factor of safety on the verge of failure. And that can be calculated from the FMLV and the COFV using the following equation. And it's called the log normal reliability index, beta ln. And yeah, you just plug this equation in. And then once you have that, if you take that beta ln term and use it as an input argument to the Excel function NORM SDIST, that will return the reliability. And you take 1 minus that number and you have the probability of failure. And so again, once you have the FMLV and the coefficient of variation on the factor of safety, it's a really simple and straightforward way to get the reliability and the probability of failure. But how do we come up with the COVF, the coefficient of variation of the factor of safety? Well, as I mentioned before, the FMLV is, we do it doing a conventional slope stability analysis. But in order to determine the coefficient of variation for the factor of safety, we've got to dig a little deeper, and there are two common approaches for doing that. One is called the Monte Carlo method, and the other would be the Taylor series method. With the Monte Carlo method, you you take your input parameters, your undrained strength, your unit weights, and you perturb them, each of them, and generate n equally likely model instances or realizations, and then you perform a slope stability analysis on each of those n models and calculate a factor of safety for each, and that gives you a large number of factors of safety. From that, you calculate the standard deviation, divide by the mean factor of safety, and you have the coefficient of variation. So here's a graphical representation of how that works. Let's say you have a cohesion, a friction angle, and a unit weight. It's just a slope with a single material in it, each of which, if this is a graphical representation of their probability distribution functions, the middle line is the mean, the spread between that and the outer lines is the standard deviation. And if we know the mean and the standard deviation, and we know that it's normally distributed, you can use a special Gaussian random number generator to randomly select a value that's somewhere on this bell curve. And if you generate a large number of them, the histogram that you generate would match this bell curve. And so, in other words, you can generate random values of C, phi, and gamma, each of which, if you do it, say, 1,000 times and then calculate the mean and the standard deviation of probability distribution, it would match your assumptions you put in. But what that allows us to do is, let's say we generate a random C, a random phi, and a random gamma. That gives us one set of parameters to use in a model or a slope stability analysis. And then we do that again and again. We come up with this big table of C, phi, and gamma values, and you just run the analysis for each of those. And then when you're done, you have a set of factors of safety, as shown here. And if you take the mean of these, you get 1.15. The standard deviation is 0.159. Divide the standard deviation by the mean, and you have a coefficient of variation. Now, I've only shown you 11 here. How many runs are required? You'd need a lot more than 11, I promise you, to get some results that make sense. Ideally, you run enough model runs that you achieve what's called statistical convergence, which is the point. For example, you can do 100 runs and then calculate the coefficient of variation, do 150 and do it again, add another 50 and do it again, and at some point, if you add more model realizations, it's not going to change your coefficient of variation much. And so that's what we call statistical convergence. The problem with this method is that generally you have to run several hundred simulations in order to get statistical convergence. And if it's a really simple problem, maybe you could automate that. But if you're having to run that multiple times in something like UTexas, that would be a lot of work. And so there's another way to do it, which requires much less work, and it's called the Taylor series method. And so instead of doing several hundred simulations, we can do maybe 6 or 10 or 12 or something like that. And the way this works is you determine the standard deviation for each parameter. And then sigma I means we're looking at I is the ith parameter. And then we calculate Fi plus and Fi minus, where Fi plus equals the factor of safety where the parameter value is equal to the most likely value, or the mean value, plus sigma I. And all of the other parameters are held constant. So in that model run, you just take that, you're looking at that one parameter, and you perturb it up by one standard deviation, and then calculate the factor of safety. That is Fi plus. And then you take that same parameter, and you decrease it by the standard deviation, hold everything else constant, and that's Fi minus. Then you take Fi plus minus Fi minus, and that's delta Fi. That's the delta Fi for that parameter. And then you repeat that for each of the other parameters. And then once you do that, you plug it into this equation. If you have n parameters, you take delta f1 over 2 squared plus delta f2 over 2 squared all the way up to delta fn over 2 squared. Add them up, take the square root, and that is the standard deviation of the factor of safety. Divide that by the factor of safety of the most likely value, and you have the coefficient of variation of the factor of safety. So here's an example. This is the San Francisco Lash Terminal, which failed in 1970, and it occurred over a 250-foot-long stretch of the trench during the excavation. So they were doing an underwater excavation to presumably make like a ship channel for a dock, and that failed. And they went back and looked at it later. So the excavated surface before failure was at a 0.875 to 1. That's a very steep slope. And then this is what it looked like after it failed. So it was fairly costly to fix that. And they went back and looked at it and recalculated the probability of failure based on the original slope angle, and then they looked at some other slope angles for when they rebuild it. And and we're going to go through some examples of this in our in-class exercise. But anyway, so here's the for the undrained shear strength and the buoyant unit weight. The factor of, excuse me, this is how they came up with the spread or the uncertainty. And for the undrained strength, they did the plus or minus line from a graphical analysis. This is figure 13.1 in your textbook. The buoyant unit weight, they had an actual sigma. And so using the average, so the two parameters they had were undrained strength and buoyant unit weight. So using the average or most likely values, they calculated a factor of safety of 1.17. And then if you hold everything constant but the undrained strength and increase it by 1 standard deviation, you get a factor of safety of 1.3. Decrease it by 1 standard deviation, you get a factor of safety of 1.02. Take the buoyant unit weight, hold everything else at the most likely value or the mean value, increase it by 1 standard deviation, and you get 1.08. Decrease it by 1 standard deviation, and you get 1.28. So your plus and your minus should always bracket, be above or below the FMLV. And then 1.33 minus 1.02 is 0.31. 1.28 minus 1.08 is 0.2. You take the absolute value of this difference. And then if you plug 0.31 into this Taylor series equation and 0.2 into the Taylor series equation, you get a standard deviation of the factor of safety of 0.184. Divide that by the most likely value, and you get a coefficient of variation of about 16%, 15.8%. And so that's this value right here. And if you plug that into that equation, that scale the value from the table we saw, or run the spreadsheet analysis, you get a probability of failure of 18%. So they had about like a 1 out of 5 chance that the slope will fail. Well, in fact, it did fail. So 18% is a little risky. But at that 0.875 slope, the volume, it's a steep slope, so the cubic yards you'd have to excavate for this trench would be 860,000. But if you go with a 1.25 slope and redo this analysis, the factor of safety most likely value is 1.3, the coefficient of variation is 16. Now notice all of these coefficient of variations are the same. That's because the strengths and the unit weights are the same for all three of those cases, so that actually turns out to be the same. But in this case, we get a 6% probability of failure. And if you go with a 1.6 slope, then you get a 1% probability of failure. Now these lower probabilities require a larger amount of material to be excavated, but certainly you can so these last two columns, if you're designing this, this is really helpful, because then you've got a kind of a direct relationship between the probability of failure or the reliability and the cost, the actual trench volume. So this is an incredibly powerful and really useful way to do slope stability analysis, and it doesn't really require that much extra work, and so I would certainly recommend doing this for any project where you're really concerned about weighing the interplay between the probability of failure and the cost and the risks associated with the failure.